Here we go, ladies and gentlemen. On the last time we were here in class, we discussed how to simplify logarithms, and we ultimately got this set of notes, which was very important for us. Log base b of y equals x. If you switch this logarithmic form to exponential form, it's b to the x equals y. So the actual thought process when you evaluate logs, especially when there's no variables involved, just numbers, nice numbers, you really take a look at the log and you look at that base and you think, this base to what power will give me this answer y? Again, this base, the base b, to what power will give me the answer y? So that's how the exponential form comes about. The base to what power gives me the answer y. Do we understand that? If we don't understand that, you're not going to be able to understand logarithms. So when I look at log base 2 of x, I'm really thinking, oh yeah, by the way, when you read these, you have to use the word base right before saying this bottom number, and you have to use the word of right before saying this big number right here. So log base 2 of 8. What you need to think is the base on the logarithm, think of it as the base of the exponent. So if you did this like in your head, you're going to be thinking 2 to what power will give me the answer 8? So 2 to what power gives you 8? 3. So that's why the answer here is 3. Does that make sense? Nice and easy, right? Okay, this next one, it requires some thought, because when you think about this base 25, log base 25 of 5, you're thinking 25 to what power gives me 5? So in your heads, you're thinking 25 to what power gives me 5? Well, first of all, when I see 25, I think of the perfect square number 25, right? Which means that the square root of 25 is what? 5. So what exponent would actually cause me to take the square root of 25? What exponent would cause me to take the square root of 25? What exponent would cause me to take the square root of 25? 1/2, right? We should remember, I hope we remember, that a square root is really the power of 1/2. You guys remember that? The third root is the power of 1/3, and so on, right? The fourth root, power of 1/4. So right here, when I'm thinking 25 to what power will give me 5? Well, to the 1/2 power, that'll cause me to take the square root of 25. My answer will be 5. So what's my answer for number 2? 1/2. That's my answer for number 2. Log base 25 of 5, the answer is 1/2. How about number 3? I really need to be thinking the base 1/2 to what power will give me the answer 8? -3. Good. So -3 is your answer right there. Because if you were to put 1/2, to the -3 power, you would distribute the -3 to the 1, distribute the -3 to the 2, and the 2 to the -3 would have to move up and become 2 to the +3, and 2 to the +3 really is 8. And number 4, that one's ridiculously easy. What's the answer there? 1. We need to remember this. Log base anything of that same something will eliminate, and the answer is just 1. It causes it to disappear. It undoes itself, right? So let's all do this one. Go over here. Number 5 on the class opener. Sorry about the mess. Find the inverse of y equals 2 to the x. This is kind of like a review problem, but not really. Because finding the inverse is something that we should already know how to do. How do we find the inverse of any function? Switch x and y, and then solve for y. Okay, so we're going to begin this thing by magically switching the y with the x. I want to take this y and put it as an exponent, and I want to take that x that's an exponent and put it as a regular x. So I have a regular x equaling 2 to the y power, right? So that's the first part of finding the inverse, switching x and y. But now we need to solve for y. How do I solve for y? See, y is an exponent. I don't want it to be an exponent. I want it to be a regular y. If I want to undo the base 2, I would have to apply a logarithm. I mean, we should know that when I do log base 2 of 2, what happens with the log base 2 of 2? It cancels out, it eliminates, and the y comes down. The y comes down. But you can't just do something on one side of the equation. You have to do it to the other side of the equation, log base 2 of x. So what do we have here? Our answer is y equals log base 2 of x. That's our inverse of the original y equals 2 to the x power. So have we graphed y equals 2 to the x before? Yeah? What would this be called? An exponential growth function. Why growth? Because the base is greater than 1. It's 2, right? That's a growth function. And we know how to graph exponential growth functions, right? Okay. Look at this exponential growth function and look at the inverse of it. Y equals log base 2 of x. Okay. What do you notice? What looks, let me see, could I move this? No, I cannot move it. What looks familiar with this guy and this guy? Just, what could you tell me of how it looks? Anybody? No. Do you notice anything of this guy and this guy?
Y equals.
They both have y equals, okay. Check this out, guys. If I take y equals log base 2 of x, and if I just magically, or not magically, if I take a finger or something, if I cover up this log, it kind of looks like y equals 2 to the x. It kind of looks like that, right? That's a very important truth, that the inverse of a basic exponential growth function or decay function, the inverse of an exponential function without h or k, will be logarithm of that same base that was on here with the x. And if I do the inverse of a logarithmic function, all you got to do is pretend that it's not a log and just pretend that it's y equals 2 to the x. And that's the actual inverse of it. Okay? That's going to come into play in a little while. Check this out. So let's jump to this worksheet right here. Our homework for today, classwork / homework, is to graph these 8 functions. And we're going to have some logarithmic functions and a couple of review questions of exponential growth or decay functions. So let's begin by graphing something very, very basic. Let's do number 2 instead of number 1 is a review question. We should know how to graph exponential decay function. All right, for funsies here, you guys can do this on your own later, but at least tell me, what's my h value, what's my k value on number 1? H is 3 and k is -5. All right, now what does that mean? That you're going to ultimately shift 3 units to the right and 5 units down once you actually have your coordinates. Coordinates of what? Coordinates of this boxed-in, boxed-in function that we're going to call the parent graph. And normally we make a XY table for these, and we use the inputs that are consecutive integer inputs, like -3, -2, -1, 0, 1, 2, 3. And we plug in the easiest input of 0 right in there, because anything to the 0 power, ignoring h and k of course, anything to the 0 power will be 1. So when I plug in 0, and there's no a value out here that you need to multiply it by, so plug in 0 right there, anything to the 0 power is 1, so your output is actually 1. And then you could plug in your other values, or you could use the growth or decay factor to get your other outputs. Because you have consecutive integer inputs, you could use and make this output of 1 decay by half, which would then become 1/2. And you can make the 1/2 decay by half, which would become 1/4. Decay 1/4 by 1/2, it becomes 1/8. And 1/16, and 1/32, and 1/64, which we know gets closer and closer to 0. In the opposite direction, you would just multiply by the reciprocal of that decay factor. So you'd be multiplying by 2/1, which is just multiplying by 2. Multiplying by 2 right here would give you a 2. Multiplying by 2, 4. Multiplying by 2, 8. Those are all coordinates. So what do I need to do with those coordinates after plotting them? Shift them where? 3 to the right and 5 down. Could we handle that on our own? Yes, I hope so, because we've done this in the past, right? Okay. And if you don't like shifting visually, if you really wanted to, you could go to each of these x and y values, and since you're shifting 3 to the right, you could add 3 to the x, and you could subtract 5 from the y if you wanted to. But then subtracting with fractions is kind of ugly, so it's better to just do the shifts. But anyways, that's a review question. Let's go to something new, like right here, a logarithmic function. Now, we just said that finding the inverse of a log is really an exponential growth or decay function. Finding the inverse of a growth or decay function is really a logarithmic function. And we came up with an amazing shortcut to find that inverse when we ignore h and k. And right here, there is no h and k, so it's even better. How could we find the inverse of this logarithmic function? You could switch x and y and solve for y, but the shortcut that we discovered on the class opener is that you could just cover up this log and make it look like a decay function. You see, now that looks like the function y equals 1/2 to the x power. Doesn't it look like that? Y equals 1/2 to the x power? Even though it's not, it's really a logarithmic function. But when I cover up the log, it looks like an exponential decay function, which we concluded that this is the actual inverse. This is the inverse of the original. Of course, when you don't have h and k's, the trick to finding the inverse is to simply cover up the log, and that's your inverse function right there. So let's graph this inverse function of that log, which is a decay function. And again, consecutive integer inputs. And we're going to plug in the easiest one, 0. And I'm not doing it to this one, I'm doing it to this one, right? Why? Because as of now, I am just ignoring that log and pretending that it's an exponential decay function, 1/2 to the x power. So plug in 0 right there. Anything to the 0 power is 1. So there's our output, 1. We're going to make this output decay by 1/2. So that will become 1/2. Decay by 1/2 becomes 1/4. Decay by 1/2 becomes 1/8. We'll even do one more. The next one, decay by 1/2 becomes 1/16. It's ridiculously close to 0. In the other direction, we're going to be multiplying by the reciprocal of that decay factor of 1/2, which ends up being times 2. So 1 times 2 is 2, times 2 is 4, times 2 is 8. What did I just find right here? I found the coordinates to what? To the inverse of the logarithmic function. I found the coordinates to this guy right here, y equals 1/2 to the x power. I did not find the coordinates of y equals log base 1/2 of x. I did not, right? However, since we know that this guy is the inverse of this guy, how do we find inverses anyway? How do we find inverses anyway? Switch x and y and then solve for y, right? So the key there, to find the inverse, you switch x and y. So if you know that these are the coordinates of the inverse of this guy, then you technically do have your coordinates. All you have to do is switch x and y. All you have to do is switch x and y. So if I want my coordinates to the actual logarithmic function, let's make an xy table over here. All I need to do is switch -3, 8, and make it 8, -3. Switch x and y. -2, 4, switch it. 4, -2. Switch x and y, 2, -1. Switch x and y, 1, 0. Switch x and y, 1/2, 1. Switch x and y, 1/4, 2. Switch x and y, 1/8, 3. Now, these guys right here are the actual coordinates of that logarithmic function. So let's review the steps that we just did. Step 1 was to cover up that log. Why? So it'll look like an exponential function, exponential decay function to be more exact, which is the actual inverse of the original. But you cover that up, you get those coordinates. Since it's an inverse, we switch all the x and y values to get our actual x and y values of the actual logarithmic function. So let's plot these points. 8, -3, 1, 2, 3, 4, 5, 6, 7, 8. -1, 2, 3 is right. Whoop, that's not it. Right there. Let's go to 4, -2. 1, 2, 3, 4. -2 is right there. And let's go to 2, -1. 1, 2, -1 is right there. Let's go to 1, 0. It's right there. Let's go to 1/2 and 1. Halfway on the x, 1 up. And then we're going to go to 1/4 on the x and 2 up. So check this out. Half is right there. 1/4 is even half of the half, so it's even closer to the y-axis. 1/4 on the x, 2 up is going to be right here. Really close to the coordinate 0, 2. Let me put my point right there. Half of the half. And then when I go to 1/8, which is half of 1/4, and then 3 up, that's really close to 0. So it's practically 0 and 3 up. It's even closer to the y-axis. Do we see what's happening here? It's getting closer to the y-axis, which means that in this direction, it's going to keep getting closer and closer to the y-axis in this case, not the x-axis. So that means that it gets closer and closer and closer. This is my actual asymptote. It's not the x-axis anymore, it's the y-axis this time. So this is my graph, ladies and gentlemen. This is my graph. Do we understand that the asymptote is right here at the y-axis, which is the x equals 0 line, the vertical line of x equals 0? Do we understand that? Okay, let's talk about domain and range here. What's the domain? Oh yeah, by the way, guys, we only used the inverse to find the coordinates to be able to switch the x and the y. Once you do that, I probably would just draw a line through it. That way you don't make the mistake of plotting those points. So the domain, is it x equals all real numbers?
No.
No. The domain is x. Now remember, the domain is the x values to the left and to the right. Does this graph go to the left forever?
No.
No, it doesn't. Look, going this way, it infinitely approaches what x value? The y-axis, which is x equals 0. So what do we say? Where's this red graph at? Is it less than x equals 0, or is it greater than the x equals 0 line? Less than's to the left, greater's to the right. So this whole thing is greater than that x value of 0. So the domain is x is greater than 0. Does that make sense?
Yes.
Yeah? Okay, how about the range? The range are your y values. Does this red graph go up forever?
Yeah.
Does it go down forever? Yes, even though it curves, it continues to go down forever. So what's the range? Y equals all real numbers. That's exactly right. Okay, so once again, to reiterate here, we know that we could find the inverse of this log base 1/2 of x. How would I find the inverse? I would switch x and y, then I would solve for y, and that would produce this exponential decay function. The shortcut of doing that is to simply cover up your log, and you could actually see it right there. Y equals the decay function 1/2 to the power of x. Y equals 1/2 to the power of x. I then find coordinates to that growth or decay function, get those points, and because that's the inverse, I switch the x and the y's. So the coordinate -3, 8 became 8, -3. I switch all these coordinates to get the actual coordinates of the original logarithmic function, and then I plot my points and I graph it. But I need to understand the graph in terms of domain and range as well. So it's really easy because right here you have no h and k, and the inverse of this logarithmic function truly is y equals 1/2 to the power of x. Now what if you did have an h and k? What if you did have an h and k, like right here? What should I do then?
Ignore it.
Ignore it. Just like always, identify h and k. Okay, so your h is 3, your k is 2. That means 3 to the right and 2 up. Once you get your coordinates, ignore the h and k, box in your function and leaving h and k out. Now, from here, it's hard to get your actual xy values, right? It's just really confusing to start plugging in values for x and pulling out values for y. It's a lot easier to think of the inverse of log base 1/2 of x. What is the inverse of log base 1/2 of x?
1/2 to the x power.
Yep, ignoring log, you see y equals 1/2 to the x power. So find the points to that exponential decay function, and then once you have those points, you switch the x and the y's to get your actual coordinates, and then you shift according to h and k on your actual coordinates. That's how you get your final graph right there. Is it Easy? Not really. It gets easy the more you practice it. It is pretty much a long process, but the true understanding here is that we know that the inverse of a log is an exponent. The inverse of an exponent is a log, and that's why we're able to get the coordinates of an exponential decay function and just simply switch them, which will give us the coordinates of the logarithmic function, and then we shift them according to h and k. So here it is, guys. If you could pause the video and jot these down. Step 1 is identify h and k. Like always, ignore h and k by boxing in the function. Step 2, cover up the log to get the coordinates of the exponential function inside the box. Step 3, switch the x and the y values to get the actual coordinates of the log function, and make sure you shift those coordinates according to h and k. So those 3 steps will get you through this whole thing. So we already did step 1. We identified h and k. We boxed in the function. We're ignoring log, so it'll look like an exponential decay function, y equals 1/2 to the x power. We're going to use consecutive integer inputs. And let's plug in the easiest one, 0. When we plug in 0, right here, it'll be 1/2 to the 0 power. Anything to the 0 power is 1. And as we go down, we're going to end up decaying it by that decay factor of 1/2. So it goes 1/2, becomes 1/4, becomes 1/8. You can keep going, 1/16, and so on and so on. In the opposite direction, it would be multiplying by the reciprocal of 1/2, which is really multiplying by 2. 1/2 times 2 is 1, times 2 is 2, times 2 is 4, times 2 is 8. So those are the coordinates of y equals 1/2 to the x power. We don't want to graph y equals 1/2 to the x power. We want to graph the inverse of this, which is log base 1/2 of x. So since we know that this is the inverse of that, all we need to do to get the actual coordinates of that would be to switch x and y. So over here, we're going to get our actual x and y coordinates. Instead of -3, 8, it's 8, -3. Instead of -2, 4, it's 4, -2. Instead of -1, 2, it's 2, -1. Instead of 0, 1, it's 1, 0. Instead of 1, 1/2, it's 1/2 and 1. Instead of 2, 1/4, it's 1/4 and 2. Instead of 3 and 1/8, it's 1/8 and 3. So let's plot. By the way, once you get those coordinates, you don't need these anymore. You could just scratch them out. So let's plot 8 and -3. So if we go 8 on the x, -1, 2, 3 on the y, we will end up right here. And then if we go 4, -2, 4 on the x, -2 on the y, right there. And if we go to the next one, 2, -1, 2 on the x, -1 on the y, right there. Go to 1, 0. That is 1, 0 right there. Go to 1/2 on the x, 1 on the y. So right here, only halfway on the x and 1 on the y. You'd end up right there at the halfway point. And then when you go 1/4 of the way, that's really half of half, 1/4 of the way, and then 2 up. So 1/4 of the way is only half of the half, which would be 2 up would even be closer to the y-axis. And closer and closer and closer. You actually draw it like if it were on the y-axis itself. The asymptote is x equals 0 if we didn't have an h or k. But once I shift all these coordinates, 3 to the right and 2 up, where's my new asymptote going to be at? At 2, exactly. No, I'm sorry. 3, at 3. Because you are shifting, see the asymptote was right here. If I shift all of my coordinates 3 to the right, that's going to be my new asymptote. So you could begin by putting your asymptote at x equals 3. And let's shift all your coordinates 3 to the right and 2 up. So this coordinate right here, 3 to the right and 2 up, I'll be off the graph, but I'm going to plot it anyway. If I go this one, 3 to the right and 2 up, I'll be right there. And move them all over, 3 to the right and 2 up. And you'll end up with this blue graph on that new asymptote of x equals 3. So what's the domain on this guy, on the actual logarithmic function? X equals, is it x equals all real numbers? No, it's not.
Greater than
X is greater than the asymptote. Where's the asymptote at?
3.
It's at 3. So x is greater than 3. How about the range? Y, it really does go up and down forever, so that really is all real numbers. And we could even take this a step further. If I were to say, as x approaches negative infinity, f of x approaches what? What does this mean? As you look at it, to the right or to the left? To the left. So you go over here and go to the left. Where are your y values going? Up forever. What's your y value here? It's -1. What's your y value here? It's 0. What's your y value here? It's 1, 2, 3, 4, 5, 6, 7, 8, 9. Your y values are going up forever. So your f of x values are approaching, your y values are approaching positive infinity. Okay. Now let's look at this to the right. As x approaches positive infinity, f of x approaches. So let's look at this visually. As you're going that way, what's it approaching on your y's? Well, you were way up here, and you start going down on your y's, down on your y's. You're at 0, you're at -1, you'll be at -2, -3. You're going to keep going down forever. So that'd be negative infinity. Okay, so we've done 2 problems. We have some review problems, some exponential growth or decay. I hope we can handle this. Let's try to do the rest of them on our own. And I'll make some other videos explaining the other ones.